In this video lesson, we're going to cover projectile path number 2. This video lesson is the third video lesson in the series covering projectile motion. So make sure you've already watched Introduction to Projectiles and Projectile Path number 1, as a lot of the concepts we'll be covering will come from those two videos. Before we start doing some practice problems, let's understand the concept and idea of projectile path number 2. Because we are still neglecting air resistance and lift, the pathway for projectile path number 2 is perfectly symmetrical. You'll see on the left-hand side of the screen there is a drawing for this pathway. There's a few things I'd like to point out as we go through this pathway. The first thing I want to point out is the fact that the object, whatever it is starting and ending at the exact same height. So the object begins and ends at the indicated height. Now you'll notice that the motion map is drawn for this object. The first part I'd like to point out is the diagonals. The diagonal arrows is what's actually taking place in real life. So let's first notice the pathway that the object actually takes. You'll notice being highlighted in red right now is the actual pathway, which is diagonal. It levels out towards the top and then starts to move downwards as it goes back to the original height. Now, if you remember from the last video lessons that we talked about, if you drew a force diagram for this object, the only force acting on a projectile is the force of gravity. Because we're neglecting air resistance and any sort of lift or drag forces that could be acting on the object, the velocity is going to change only in the y. The x velocity is going to remain the same. That's why you can notice if we split up those diagonal vectors, the x velocity is going to be the same length at every point of the projectile path. Now, because this is a perfectly symmetrical pathway, we can get a lot of information from this pathway if we just drew a line right down the center. Because it's perfectly symmetrical, and we are assuming that the initial and the final height are the same, the angle and the velocity are conserved. What that means is this. Let's first talk about the angle. If the angle of launch is 60 degrees, that also means the angle at which the object lands will be 60 degrees. Now let's talk about the velocity. If the velocity is fired at 20 meters per second, for example, the object will land at 20 meters per second. Now, we already know that the x velocity will not change. The x velocity remains the same because there are no x forces in the force diagram. However, the y velocities, you'll notice, are getting shorter as you go up. And then as the projectile reaches the top, there's no y velocity, and then they start to get longer as you move down. Because it is a perfectly symmetrical pathway, the y velocity will be the exact same as initially as it is finally. One last final thing is that since the y velocity is changing direction, first it was going up, now it was going down, it's very important that you establish a positive direction. For me, typically what I will do is I will make up the positive direction. That means the y velocities are positive for the first half of motion, and the y velocities will be negative for the second half of motion. Let's look at one more image before we move on to some example problems. The image on the left is very similar to what we just saw, but now it has some numbers. You'll notice this boy is throwing a ball, and it has the velocities tracked throughout its projectile path. Now, first of all, you'll notice the ball is the same height here as it is here. First, let's focus on the x velocities. The x velocity is 12 meters per second all the way through, regardless of where it's at in the projectile path. The y velocities, however, are changing. It starts out with an initial velocity of 19.6, then it slows down to 9.8, and then finally it reaches 0 at the top because it stops moving. As it moves down, notice the magnitudes are still the same, 9.8 and 19.6. However, they are negative. That's because up is the positive direction. So since up is the positive direction and velocity is facing down as it goes back down, that is why they will be negative. On the animation to the right, it's showing the same thing, however, just with motion. You'll notice that the x velocity is a constant 60 meters per second the entire time, but as time goes on, the y velocity is going to be changing. The y velocity will have an initial velocity, and it will start to decrease, reach 0 at the top, and then turn into negatives as its pathway goes further and further down. Now notice the velocity is the same as it was initially at the exact same height. It will be 60 but negative right there as it matches up with where it launched. And it just keeps increasing in velocity as it moves further and further down. Knowing this, let's go ahead and do some practice problems. Okay, consider this example number 1. A football is kicked off the ground with a velocity of 15 meters per second directed 30 degrees above the horizontal. The football lands some distance x from the spot where it was kicked. The football lands the same height as it was kicked from. We're asked to solve for 3 questions. A, how long is the football in the air for? B, how far away is it when it lands? And C, what is its final velocity when it hits the ground? Okay, first thing we want to do for any projectile problem is we want to draw a picture so we can understand the idea of what's going on. So I know that this football is being kicked from an angle of 30 degrees to the horizontal, and it travels and it lands the same ground at which it was kicked from. So it's projectile path number 2, which means the angle is conserved as well as the initial velocity. We're told the initial velocity is 15 meters per second. Now, contrary to projectile path number 1, this velocity of 15 meters per second is diagonal, which means that 15 meters per second is going to have x and y component. But since it's a perfectly symmetrical pathway, I know it will also land at 15 meters per second, 30 degrees to the horizontal. Now that we know that picture, let's now go ahead and figure out and solve for our x and y table. Remember, we need to know what the initial is, final, acceleration, time, and then displacement, both in the x and in the y. First of all, we need to figure out what is the initial velocity in the x and y. Since our velocity given is both x and y because it's diagonal, we need to split that up. So what I'm going to do is I'm going to do that off to the side here. I know that it's 15 meters per second is the hypotenuse. I want to figure out what is the x component of velocity and what is the y component of velocity, knowing that my angle is 30 degrees. First, let's find the x component. The x component is going to be 15 meters per second times the cosine of 30 degrees. If I solve for that, make sure your calculator is in degrees. The cosine of 30 times 15 is going to give me an x velocity initially of 13 meters per second. And so that's what I will plug in to my x column for initial velocity. Now, since there is no acceleration ever in the x direction, that also means my final velocity in the x will be 13 meters per second. Now let's figure out the initial velocity in the y. The initial velocity in the y is going to be found by taking my hypotenuse of 15 meters per second times the sine of 30 degrees. Sine of 30 degrees is 0.5 times 15, and so that will get me an initial velocity in the y of 7.5 meters per second. Now, remember, this is a perfectly symmetrical pathway. So if the initial velocity is 7.5 meters per second in the y direction, that also means the final velocity will have the same magnitude of 7.5 meters per second. However, remember, you need to establish which direction is going to be positive, up or down. I'm going to make up positive, which means this initial velocity is facing up, is positive, and this final velocity would be negative. So in my XY chart, I'm going to make this negative 7.5 meters per second as the final y velocity. Now my acceleration is always 10, but acceleration points down towards the Earth. Since acceleration is pointing down and I'm making up the positive direction, that means my acceleration will be negative 10 meters per second squared. The time is unknown. I do not know how far in the x direction that the object goes, but I do know what the displacement in the y is. Since it started and ended at the same height, my displacement in the y is actually 0, because it is on the same height that it started with. Now that we know all that information, let's go ahead and solve our questions. Letter A asks how long is the ball in the air for, or in other words, it wants time. Now remember, time is the same for both columns, but which column information do we want to use? Since time is dependent on y values, because the ball is in the air and it's gravity that pulls it down towards the Earth again, we need to use the y values to figure out what our time is going to be. I know all my y values except for time. When I think about the two formulas that have time in them, there's this one, which is our kinematic equation number 1, and then there's also this one, which is kinematic equation number 3. Both of them have time, and we have the information for both. I'm going to go ahead and, oops, it's not cubed, it's squared. I'm going to go ahead and use the first one because that would require me not to have to use the quadratic formula. So, to find out time, my final velocity in the y direction is negative 7.5 meters per second. Remember, I'm using all y values. That's equal to my initial velocity is positive 7.5 meters per second, plus my acceleration is negative 10, and then times t. If I start to simplify that to get my answer, what I'm going to do is I'm going to take this positive 7.5 and subtract it from both sides. Doing that is going to get me negative 15 meters per second is equal to negative 10 t, and I'm going to divide both sides by negative 10. That will get me my time of t equals 1.5 seconds. Now let's look at letter B. Letter B asks how far away is it when it lands? Move some of this information. When it asks for how far away is it when it lands, it's asking for x. Since it's asking for x, I need to use x values in order to solve for this. What I'm going to end up using is I'm going to use my formula for velocity that's rearranged. X equals v initial times t. It's important to note that this is actually coming from kinematic equation number 3 that looks like this. However, I'm able to get rid of this second term because the acceleration is 0 in the x direction. And we went over this in projectile path number 1. So to figure out how far the object went, I'm going to take my initial velocity in the x direction, which is 13 meters per second, times the time it's in the air for, which I now know is 1.5 seconds. Multiplying those two together, I'm going to get my distance is 19.5 meters. The final question is, what is its final velocity when it hits the ground? Remember, this is a perfectly symmetrical pathway. So if it initially was shot at 15 meters per second, its final velocity will also be 15 meters per second. The way we would justify our answer for this is not using math, but using logic. So what I would want to do is I would want to explain how I know it's 15 meters per second. And that is, since there is no x forces and the initial and final height is the same, then the velocity is conserved. So that completes our first example problem. Now let's go ahead and look at a second example problem here. This problem is set up a little bit differently. In this problem, we're going to go ahead and draw a picture first, and then fill out our XY chart to figure out what we need to do to solve for A and B. The situation is a cannonball is launched at an angle of 35 degrees. It's in the air for 4.5 seconds and lands 15.5 meters away from its launch point. What was the initial velocity, and how high does the object go in the air? We're assuming that it launches and lands at the same height since it doesn't specify anything differently. So to draw our picture, we know that it's launched at an angle of 35 degrees, which means it will land also at 35 degrees. It follows projectile path number 2, and it's in the air for 4.5 seconds and lands 15.5 meters away from its launch point. So first thing I want to do is I want to set up my X and Y chart. My V initial, V final, acceleration, time, and displacement is what I'm going to figure out whether or not I know. The question does not tell me anything about the initial velocity. So my initial velocity in the X, both initial and final, is unknown. I always know the acceleration in the X is 0. I do know that the time is 4.5 seconds, and the displacement in the X is 15.5 meters. In the y direction, I also do not know what the initial is or the final is. I do know that the acceleration is 10, and if I make up the positive direction, it's going to be negative 10, because acceleration always points down towards the Earth. The time is the same in x and y, so 4.5 seconds. And remember, since it starts and ends at the same height, my displacement in the y must be 0, because it started and ended at the exact same place in the y direction. The first question is asking me, what was the initial velocity for this object? Okay, in order to know what the initial velocity is, I need to know either what is the x component or what is the y component. Since I know my x displacement and I know what my time is, I could solve for what my initial velocity is in the x direction. So let's go ahead and do that. I know in the x direction the object travels 15.5 meters, and it takes 4.5 seconds to do that. So I could solve for my initial velocity in the x direction by taking 15.5 divided by 4.5. And if I do that, my initial velocity in the x direction is equal to 3.44 seconds. So to find my initial velocity, I now know that not only is it at an angle of 35 degrees, but it's at an angle of 35 degrees such where the x component of that velocity is 3.44 meters per second. So I'm trying to find the hypotenuse, and I'm given the adjacent. So I'm going to use cosine. So I'm going to continue this work down here. The cosine of 35 degrees is equal to the adjacent, which I now know is 3.44 meters per second, over the hypotenuse, which is the initial velocity. By rearranging that, my initial velocity would be equal to 3.44 meters per second divided by the cosine of 35 degrees. All I did was just do a little rearranging to solve for V initial. So let's go ahead and do that. 3.44 divided by the cosine of 35 degrees. And provided that I'm in degrees, my initial velocity is equal to 4.2 meters per second. That is the initial velocity that is diagonal right there. All right, now let's go ahead and solve for letter B. How high does the object go in the air? So in other words, it wants to know what is its max height, which is right there at the top. Now, what do we know about the condition of the object when it's at its max height? Well, we know it's at its max height when the velocity in the y direction is equal to 0. Because remember, at the top of the pathway, and we can go back, at the top of the pathway, there is no y velocity. So it's 0 at that point. So in order to answer letter B, how high does the object go, we're just going to solve for it in such a way where we know that the final velocity in the y is 0. So let's go ahead and do that. This is B down here. I know that the initial velocity in the y direction is something I can solve for. The initial velocity in the y direction is going to be this part right here. I know the hypotenuse is 4.2, and this side right here is the opposite. So by doing sine of 35 degrees times the hypotenuse, which is 4.2 meters per second, I can figure out what my V initial in the y is. Sine of 35 degrees times 4.2 gets me an initial velocity in the y of approximately 2.4 meters per second. Now, that's initially when it's taken off from the ground. When it reaches the top of this of the arc, the final velocity in the y at that point will be 0. I know the acceleration is going to be negative 10, and so I can solve for y using my kinematic equation number 2, which is this one right here. V final squared equals V initial squared plus 2 times a times y. The V final at the top is going to be 0. That's equal to the V initial, which I have to use the y value of what we just found is 2.4 squared plus 2 times the acceleration is negative 10 times y. Let's go ahead and simplify that. 0 squared is 0. That's equal to 2.4 squared, which is 5.76. Plus 2 times negative 10 makes this minus 20y. Bringing the 5.76 over, I get negative 5.76 equals negative 20y. And I divide both sides by negative 20 to get what my y value would be. Negative 5.76 divided by negative 20 is going to get me a y displacement of 0.288 meters. So not very high. This concludes the video on projectile path number 2.